Welcome students to the fifth lecture on determinant. As I said towards the end of the last lecture that in this class I will be talking about matrix inverse. However, before going into discussing matrix inverse, let me solve one problem on determinants. What is the determinant of A is equal to A square A cube minus 1 A to the power omega A to the power 2 omega A to the power 3 omega minus 1 and A to the power omega square A to the power 2 omega square A to the power 3 omega square minus 1, where omega is cube root of unity, and we know that one plus omega square is equal to 0. If we look at the matrix, we see that all the elements in the third column is actually summation of two quantities A cube and minus 1, A to the power 3 omega and minus 1, and A to the power 3 omega square minus 1. We know that in such situations we can write the determinant as sum of two determinants, and we do exactly that one. Therefore, the determinant of A is equal to determinant of A square A cube A to the power omega A to the power 2 omega A to the power 3 omega and A to the power omega square A to the power 2 omega square A to the power 3 omega square minus the determinant of A square 1 A to the power omega A to the power 2 omega and 1 A to the power omega square A to the power 2 omega square and 1. Therefore, the determinant of original matrix A I have written as determinant of the difference between the determinant of this matrix and the second matrix. Let us call them A 1 and A 2. Now, determinant of A 1 is equal to, if we look at it, we can take A common from the first row, we can take A to the power omega common from the second row, and we can take A to the power omega square common from the third row. Therefore, if we take the terms out, what we get? A dot A to the power omega dot A to the power omega square into determinant of. Now, if we take A out of the first row, it becomes 1 A square. If I take A to the power omega out of the second row, it becomes 1 a to the power omega, a to the power 2 omega, and if I take a to the power omega square out of the third row, it becomes 1 a to the power omega square into a to the power 2 omega square is equal to a to the power 1 plus omega square into determinant of 1 a square, 1 a to the power omega, a to the power 2 omega, and 1 a to the power omega square, a to the power 2 omega square. Since this quantity is equal to 0, therefore, determinant of A 1 is equal to determinant of 1 a square, 1 a to the power omega, a to the power 2 omega, 1 a to the power omega square, a to the power 2 omega square. Now, determinant of A 2 is equal to determinant of A square 1, a to the power omega, a to the power 2 omega 1, a to the power omega square, a to the power 2 omega square, and 1. Now, if we check matrix A 1 and matrix A 2, we find that we can get A 2 from A 1 by first interchanging column 1 with column 3. Therefore, this 1 1 1 goes here and this column comes as the first column. After that, if we swap these two, then we get this matrix. Then interchanging column 1 and column 2. We know that if we interchange two columns or two rows, then determinant remains the same in the absolute value, but its sign changes. Therefore, with each interchange there is a change of a sign from plus to minus. Since we get A 2 from A 1 by two interchanges, determinant of A 2 is equal to minus 1 square determinant of A 1, or determinant of A 2 is equal to determinant of A 1. Therefore, determinant of A is equal to determinant of A 1 minus determinant of A 2 is equal to 0. Any matrix whose determinant is 0 is called a singular matrix. Likewise, a matrix with non-zero determinant is called a non-singular matrix. The concept of singular and non-singular matrix is very important in computing inverse of a matrix. So, if A is a non-singular matrix, we can find another non-singular matrix actually both of them are square matrix, because we are talking about their determinants. So, when we are talking about the other matrix B of the same dimension or of the same order of A, such that A multiplied by B is equal to B multiplied by A is equal to identity matrix of order n, where A and B are n cross n matrices. Question is how to obtain A inverse given a n cross n matrix A. In this lecture, we shall look at computing A inverse with the help of determinants. We shall compute A inverse with the help of determinant of A and adjoint of A. All of you are familiar with adjoint of A, because in the last lecture we have discussed it in detail. We know that A into adjoint of A is equal to determinant of A into I n. Therefore, A into adjoint of A divided by determinant of A is equal to identity matrix. Therefore, we obtain a matrix adjoint of A upon determinant of A such that A times adjoint of A and by determinant of A is equal to identity, and similarly adjoint of A upon determinant of A is equal to multiplied by A is equal to identity. Since A is non-singular, determinant of A is non-zero. Therefore, division by determinant of A makes sense, and therefore, this way we can get hold of a matrix, namely adjoint of A divided by determinant of A, such that which when multiplied by A either pre multiplication or post multiplication, it gives identity. Now, question is, can there be two inverses of a matrix? Answer is no. Why? If possible, let B and C be two inverses of A. Therefore, A times B is equal to B times A is equal to identity, and A times C is equal to C times A is equal to identity. Therefore, C is equal to identity matrix multiplied by C is equal to B times A multiplied by C is equal to B times A multiplied by C is equal to B times identity is equal to B. Therefore, we get C is same as B, or in other words, the two inverses of A are equal. This shows that we can have a unique identity corresponding to each non-singular matrix, say called A. And we have seen that we can compute that identity matrix, or we can find that identity matrix by computing the adjoint matrix corresponding to A and dividing it by the determinant of A. An interesting result: what is the inverse of AB, where A and B are two n cross n matrices? We know that A B multiplied by B inverse A inverse is equal to A B B inverse A inverse is equal to A I A inverse is equal to A inverse is equal to identity. Therefore, we can say by uniqueness of inverse that A B inverse is equal to B inverse multiplied by A inverse. Another result: if A and B are non-singular matrices then adjoint of A B, the product matrix, is equal to adjoint of B multiplied by adjoint of A. Proof: consider A B times adjoint of B into adjoint of A is equal to, by associativity of matrix multiplication, A multiplied by B times adjoint of B multiplied by adjoint of A. Now, we know that B into adjoint of B is equal to determinant of B into identity. Into adjoint of A is equal to determinant of B into A multiplied with identity multiplied with adjoint of A is equal to determinant of B multiplied by A into adjoint of A is equal to determinant of B into determinant of A into identity. Since adjoint of AB is such that AB multiplied by adjoint of AB is equal to determinant of AB into identity. Therefore, is equal to determinant of A into determinant of B into identity. Therefore, we find that AB into adjoint of AB is equal to AB into adjoint of B into adjoint of A is equal to determinant of A into determinant of B into identity. Therefore, by multiplying both sides with AB inverse, we get adjoint of AB is equal to adjoint of B into adjoint of A. Let me give an example. Compute the inverse of A is equal to 1 minus 1 2 0 2 minus 3 3 minus 2 4. Now, determinant of A is equal to 1 into 2 into 4 minus minus 3 into minus 2. If I expand along the first column, plus 3 into minus 1 into minus 3 minus 2 into 2 is equal to 8 minus 6 plus 3 into 3 minus 4 is equal to 2 minus 3 is equal to minus 1. Therefore, A is non-singular. Since this is not equal to 0. Therefore, we can compute A inverse by computing first the adjoint of A and then dividing it by the determinant, namely minus 1. Now, A is equal to 1 minus 1 2 0 2 minus 3 3 minus 2 4. Therefore, A 1 1 is equal to 4 into 2 minus 3 into minus 2 is equal to 8 minus 6 is equal to 2. A 1 2 is equal to cofactor of this is equal to minus 1 whole to the power 1 plus 2, 0 into 4 minus 3 into 3 is equal to minus 9. A 1 3 is equal to 0 into minus 2 minus 3 into 2 is equal to minus 6. A 2 1 is equal to minus 4 minus 2 into minus 2 is equal to 0. A 2 2 is equal to 4 into 1 minus 3 into 2 is equal to minus 2, and A 2 3 is equal to minus 1 to the power 2 plus 3 multiplied by 1 into minus 2 minus 1 into 3 is equal to minus 2 plus 3 is equal to minus 1. A 3 1 in a similar way is equal to 3 minus 4 is equal to minus 1. A 3 2 is equal to minus 3 minus 0. So, minus 3, but the sign will change, therefore, plus 3, and A 3 3 is equal to 2 minus 0 is equal to 2. Therefore, adjoint of A we get by writing the transpose of that matrix is equal to 2 minus 9 minus 6 0 minus 2 minus 1 minus 1 3 2. Therefore, A inverse is equal to, we get by dividing this by minus 1, and therefore, that is going to be minus 2 0 1 9 2 minus 3 and 6 1 minus 2. Verify that A times A inverse is equal to I 3, that is identity of order 3, and A inverse dot A is also I 3. This I leave as an exercise for you. Now, the question is, what is the determinant of A inverse? That means, if we have the determinant of A, then what is going to be the determinant of A inverse? We know that A into A inverse is equal to identity. Therefore, determinant of A into A inverse is equal to determinant of I is equal to 1. Now, since determinant of product is equal to product of the determinant, therefore, determinant of A into determinant of A inverse is equal to 1, or determinant of A inverse is equal to 1 upon determinant of A. Therefore, if we know the determinant of A, then we know that its reciprocal is going to be the determinant of the inverse. Example, what is the inverse of A is equal to 1 0 0 0 cos alpha sin alpha and 0 sin alpha minus cos alpha. We need to compute the inverse of this matrix. How do you do it? So, we first compute the cofactors of A. A11 is equal to cos alpha into minus cos alpha minus sin alpha into sin alpha is equal to minus cos square alpha minus sin square alpha is equal to minus 1. A12 is equal to 0 times minus cos alpha minus 0 times sin alpha is equal to 0. A13 is equal to 0 times sin alpha minus 0 times cos alpha is equal to 0. A21 is equal to 0 times minus cos alpha minus 0 times sin alpha is equal to 0, a 2 2 is equal to minus cos alpha minus 0 is equal to minus cos alpha. In a similar way, A23 is equal to minus 1 to the power 2 plus 3 into 1 into sin alpha minus 0 is equal to minus sin alpha. A 3 1 is equal to 0 into sin alpha minus 0 into cos alpha is equal to 0. A 3 2 is equal to minus 1 times 1 into sin alpha minus 0 is equal to minus sin alpha, and finally, a 3 3 is equal to sin alpha. 0 in a 3 3 is equal to 1 into cos alpha minus 0 is equal to cos alpha. Therefore, adjoint of A is equal to minus 1 0 0 0 minus cos alpha minus sin alpha 0 minus sin alpha cos alpha. Therefore, A into adjoint of A is equal to 1 0 0 0 cos alpha sin alpha 0 sin alpha minus cos alpha multiplied by minus 1 0 0 0 minus cos alpha minus sin alpha 0 minus sin alpha cos alpha is equal to first row first column is equal to minus 1, first row second column is equal to 0, first row third column is again 0, second row first column is equal to 0, second row second column is equal to minus cos square alpha minus sin square alpha, and second row third column is equal to minus cos alpha sin alpha plus cos alpha sin alpha. Third row first column is 0, third row second column is equal to minus cos alpha sin alpha plus cos alpha sin alpha, and the third row third column is equal to minus sin square alpha minus cos square alpha. Therefore, A into adjoint of A is equal to minus 1 0 0 0 minus 1 0 0 0 minus 1, that is minus 1 times identity of order 3 is equal to determinant of A into identity of order 3. Therefore, also we can calculate the inverse of A is adjoint of A divided by determinant of A is equal to minus 1 0 0 0 minus cos alpha minus sin alpha 0 minus sin alpha into cos alpha whole divided by minus 1 is equal to 1 0 0 0 cos alpha sin alpha and 0 sin alpha minus cos alpha. So, this is the inverse of the given matrix. I want you to verify that A into A inverse is equal to A inverse into A is equal to identity matrix. Let me do another example. Show that the matrix one, 2, 2, 2, 1, 2, 2, 2, 1 satisfies the equation A square minus 4A minus 5 times I 3 is equal to O, where O is the 0 matrix of order 3 cross 3. Also, find out the inverse of the above matrix. Let me call it A. Since A is equal to 1 2 2 2 1 2 2 2 1, A square is equal to A into A is equal to 1 2 2 2 1 2 2 2 1 multiplied by 1 2 2 2 1 2 2 2 1 is equal to 9 8 to 8 8 9 8 8 8 9. Therefore, A square minus 4A is equal to 9 8 8 8 9 8 8 8 9 minus 4 times 1 2 2 2 1 2 2 2 1 is equal to 5 0 0 0 5 0 0 0 5 is equal to 5 times the identity matrix of order 3. Therefore, a square minus 4a is equal to 5i. Therefore, a square minus 4a minus 5i is equal to 0 matrix of order 3 cross 3. Therefore, a square minus 4a is equal to 5i. Pre-multiplying by A inverse, A inverse into a square minus 4a is equal to 5 times A inverse into I, or A minus 4 into identity matrix is equal to 5 times A inverse. Therefore, A inverse is equal to A minus 4 times identity matrix divided by 5 is equal to 1 2 2 2 1 2 2 2 1 minus 4 0 0 0 4 0 0 0 4 divided by 5 is equal to minus 3 2 2 2 minus 3 2 2 2 minus 3 divided by 5 is equal to minus 3 by 5, 2 by 5, 2 by 5, 2 by 5 minus 3 by 5, 2 by 5, 2 by 5 minus 3 by 2 by 5 minus 3 by 5. So, once a matrix equation is given like this, we could very easily compute the inverse of the given matrix A. I want you to verify A into A inverse is equal to A inverse A is equal to identity. I finished this lecture with a tricky question. What is the determinant of adjoint of A when determinant of A is given? We know determinant of A into adjoint of A is equal to determinant of A into determinant of adjoint of A is equal to determinant of A into identity of order n, where A is n cross n, is equal to determinant of A into identity of n, where A is n cross n, is equal to determinant of this matrix that is identity multiplied by determinant of A of the order of n cross n is equal to determinant of A whole to the power n. Therefore, determinant of A into determinant of adjoint of A is equal to determinant of A to the power n. Therefore, determinant of adjoint of A is equal to determinant of A whole to the power n minus 1. Therefore, determinant of adjoint of A is equal to determinant of A to the power n minus 1 whole to the power n minus 1. Therefore, given a matrix A, we can compute determinant of A inverse, determinant of adjoint of A, and also determinant of adjoint of A. Okay, friends, I stop here today. In the next class, I shall show some application of determinants, particularly in solving systems of linear equations. Thank you.